Start streaming.
All right, we're live.
Clemens, do you have any broadcastable news?
Yes, I have broadcastable news.
Broadcast it.
Okay, good. So next week there's the away day. And for the people who are going to the away day, it would be still good to give a presentation. And there was a call for presentations on the away day topic on Zulif, but I will resend this after the talk. But you should send me by Monday just the title of your lightning talk. And your lightning talk should not be an overview of yourself, just one fact that you want to present to the world.
What
In
if
5
I don't want to
minutes.
present anything to the world?
Something cool. If you don't want to, then don't do it. But it's not obligatory. But I think it would be good. Encouraged. I don't think we can give anybody spider credits for it.
What?
What?
Maybe I can just threaten that if nobody submits anything, I will talk 20 minutes about Stone Duality. So far we have, really? Okay, yes. But it's already online, so. I should say that we have already some submissions, and we had actually one person who submitted more or less on the day when it was published as a code, which the person can't be named due to GDPR reasons, obviously. I think Fred's title just doesn't tell me anything, and I really forgot again. Sorry, let's not go there now. What are we doing now is the question, right? Any other news? Maybe to save the day? But indeed, next Friday is the away day, in case this news has been forgotten. Are you going to go to the away day? Yes? Okay.
I've asked the venue whether there are showers, if people want to cycle there, but I haven't heard back.
Are we sure that we have a venue?
Yeah, we have a venue. You can take my bike.
Only trains. What's the kind of same train?
Yes, we can organize plans with us.
Yeah.
But the overall plan is everyone buys their own ticket.
Okay. Good. Then what? Let's start with the talk. So the talk today will be about basic stone duality. So this is intended to be a proper 101 in the sense that I'm not going to give any kind of overview of current research, but just something that I should know much better. But I have a feeling I could have given that same talk with much more knowledge 20 years ago. That is kind of the disclaimer I have, is that the preparation of this talk was kind of frustrating because I realized that I forgot most of the things that I knew at some point. But anyway, let's try to collect ourselves. So this will be, however, basic stone duality in terms of really just the original duality, I think, which is the duality between stone spaces and Boolean algebras, which means that since then this has been, there are ample of variations of it, but this is just the classical setting. It's also not there is a version of it, it's just the set-based setting, so we are not talking about point-free topology, for example. So there's the point-free version of it, which you can look up in the Johnston book, but today it will be just very classical. There is even though this is not a research talk, there is a kind of researchy motivation of this, because I noticed indeed that more and more people are interested into constructive intuitionistic modal logic and approaches for this. And the original, so duality is important from a logical perspective, which hopefully we can convince ourselves. But the problem is that the duality that I'm going to present is inherently classical. And so there are approaches that tries to make the duality, and successfully actually do this, constructive. And this is this thing that I originally was thinking of maybe talking about. But then I realized I have to actually remind myself of the details of the classical case before I fully can appreciate the constructive one. So that's why I try to talk today about the classical case. Okay. So the first thing is, if we talk about stone duality, I said it's the duality between Boolean algebras and stone spaces. The first question is, what are Boolean algebras? And of course, we could now go into, I don't know, quite some detail. Probably I should not, but let's think about it. What's a Boolean algebra? So a Boolean algebra is just an algebra of the form. So you have a set B, you have a conjunction, disjunction, you have a negation, 0, 1. And in some sense, you can think of it as like classical propositional logic in algebraic shape. So these are two binary operations, unary operation and two constants. Now, so defining it is not very brief, but let's briefly have a look at some of the elements. So such that, so first of all, the B and OR is a lattice. So I don't know whether you want me to define what a lattice is. I have the axioms here basically, but so what? Sorry.
Distributive.
No, yeah. So okay, you're right. But I wanted to come to that in the second. So basically, first of all, this is a lattice. Then indeed, it's a bounded distributive lattice, and then we also have the negation basically. So these are the three things I wanted to say. So lattice is basically that these two are commutative, then idempotent, and you have the associativity and of course the absorption law. So the absorption law is maybe the only one which is always a bit of less in our minds, but I don't think we need it, but I write it down anyway. This is the law that if you have x, then this is equal to x or x and y. And plus other axioms, but this is one of them. Okay. Then Boolean algebras, indeed, so that we also have indeed that this here, and I chuck the 0, 1 with it, is a distributive lattice. Sorry, we didn't have distributivity before, but is a distributive lattice where distributivity is just that you have x and y or z is the same as x and y or x and z. There's another way of writing the distributivity, but apparently this is equivalent. I mean, so you could come up with distributivity by writing or here and there, but it's enough to assume one of the two. And actually, so what this is normally called is a bounded distributive lattice, where it's just a distributive lattice which has a least in a greatest element. And however, we need, of course, some axioms for those elements. So, okay, now I am exactly slightly confused about something, but let me not tell you. I'm feeling like now in a class where I know that something is fishy, but none of the students is asking me what it is. Anyway, let's.
What's the order? If you have least and greatest?
The order is easy. But actually, your question solves my problem, I think. So X is. So if you have a lattice, so if you want to know that introduction to lattice theory, which is kind of the ideal one for this kind of theory, then you go to the Stone Space book by Johnston. The first chapter is mainly just lattice theory. And so you then know that a lattice is actually, the definition of a lattice like this is equivalent to defining lattice as a partial ordered set, where each two elements have at least and the greatest bound, so to speak. And so however, if we start here, we can get to the order by saying this is smaller or equal than y, if and only if and now I'm sure I'm getting it wrong. Let's say x and y equals y. I hope this works.
No.
X. I just made it to have kind of the audience participating. I knew I would get it wrong. Anyway. No matter what I would write, right? So you have an order, and we will see in a second that, yeah. So now we need axiom for 0 and 1. Okay. So here is the sum. Okay, no. Let me not go there. So we have the axioms for the 0 and 1 that says, namely, that x and 0 equals 0, and x or 1 is equal to 1. So this is what we need, and we need, of course, that negation, basically, that x and not x equals 0, and x or not x equals 1.
First here is really fun.
Indeed.
Ooh.
You're right. So that's why what I did was a bit fishy, because saying 0, 1 is a bounded distributive lattice already assumes these two. So indeed I should kind of put those here in a sense.
Does it? How do you get to x or 1 equals 1 then?
Absorption. X or 1 equals x.
The danger.
X and 1 equals x and x or 1, which by absorption equals x.
I should say that the danger of this stuff is that this kind of arguments can completely lead you into the woods, and you will be here at 6 o'clock discussing this still. But okay, you're right. So this is we now know what a Boolean algebra is. Fantastic, right? Good. Let's briefly check whether we know what a Boolean algebra is by just playing the fantastic game BA or not. Probably it's not going to take off as a game show, right? But anyway.
To BA or not to BA?
So suppose we have this one element here, which is both 0 and 1. Is it a Boolean algebra or not? Probably the most controversial example I have.
This is a bad example.
And is it a BA or not? I mean, with a lot of stomach pain, I also think that is yes, indeed.
It is what your current definition accepts.
Yes. This is a Boolean algebra. Now the most...
The same way that the empty set is a set.
Yeah.
And it's not just in the same way, but it's literally in the same way by duality.
Yes.
Anyway, sorry. 0 and 1. This is what? I mean, this is kind of the Boolean algebra. How would we express that this is the Boolean algebra? Indeed, this is the initial Boolean algebra. Okay, so then we have still one more. Let's do this one. Now let me slightly deviate. So we have here 1, A, B, C, and a 0. Is this a Boolean algebra? Yes. Okay, negation is tricky, but even more than that, in a sense that it's not even a distributive lattice. So there are kind of these two very small lattices, which are the kind of check whether your lattice is distributive or not. If it can embed into your lattice, it's not, I think. That is the one. The other one is like this kind of pentagon thing.
Famous pentagon.
Indeed. Anyway, so this one is not, because it's, first of all, negation is a problem, but also not a distributive lattice, so to speak. Okay, let me see, is there anything else interesting? However, let's briefly, the last one, where we have 0 and 1. Is this a Boolean algebra? It's not a Boolean algebra. Is it a distributive lattice? If this is a distributive lattice, do we know more about it than this? So there's something between distributive lattice and Boolean algebra, which would be the Heyting algebras. And this is still a Heyting algebra. All of the linear ones are Heyting algebras. And I'm not even sure, but are they? I wanted to double check it in the morning. I think these linear structures, they are kind of axiomatized as the Heyting algebras that satisfy Fred's favorite formula or something. Namely that A implies B or B implies A, but I'm not sure. Yes, indeed. But I did not double check this, but I think that's true. Okay, so this is our BAs. Now, what do we want? We actually want we want to go to the next question, namely concrete Boolean algebras. So what do I mean with concrete Boolean algebras? So these are nice, right? But this is just abstract nonsense in the sense that, okay, we have a set, we have this join and meet, and we kind of draw the lattice. But what are kind of concrete manifestations of Boolean algebras? And a very natural candidate for such a concrete Boolean algebra is, given a set, we take the collection of subsets of that set. So we take the power set of X. So this is just some arbitrary set. So this is a collection of subsets. Then we take as a, did I just, yeah, okay, good. This is intersection and union. I don't know, I never know how to do complement. I just write this on top. And then finally, what do we need? We need 0, which is the empty set, and the full set. So these are kind of concrete Boolean algebras, as I would call them. And so one thing you might already, if you're coming from category theory, say that probably there's a slight mismatch in the sense that the power set monad, at least, is kind of tightly linked not to Boolean algebras, but to semi-lattices. So how likely is it that these are the Boolean algebras? Probably not very likely, but let's, so the question is, is any Boolean algebra B isomorphic to a concrete one? And what's the answer to this question?
Sorry, we mean it's a given.
Okay, is any given, sorry, that's what I mean by any indeed. I don't mean all of them are isomorphic to one.
And also, you also don't mean that there is one which is isomorphic to one.
Oh, okay, I mean, this is ridiculous. Okay, I'm gonna, is any given, no. The question is,
Are all.
no. What I'm gonna do is different. Let B be a Boolean algebra, an arbitrary, can we find X in set such that B isomorphic power set of X? Question mark. In the, sorry.
Both are good questions.
Yeah, so this is not a bad question, but I don't know. I think the answer also for the set sense would be no, but I mean, I want to have BA isomorphism. But my hunch is that even in the set sense,
Yeah, no,
the answer will be the
very
same.
false.
Okay, good. Anyway, so the answer is no. How do we prove it?
Actually, I think this is a good method for proving it.
What?
Find a countable infinite Boolean algebra.
But why does it prove it?
Because there were no countably infinite power sets.
Ah.
That's counter to the theorem.
Yeah, no, but I think I don't want to go this way. Because I don't like set theory.
You don't need set theory for it. You can just use.
You need counter theorem. I mean,
You need Cantor's theorem and you need Löwenheim's golem, and then you're done.
Okay, fine. Only these things, right? So the answer is, in any case, no. But actually, I'm a bit worried because I don't have a proof, and I realize.
I mean, there's another nice way of
But I mean, I do have a. Sorry.
I don't have but ours is the monad, the algebras are not equivalent to the algebras.
Ah. Oh wow, there's another one indeed, because it's the wrong monad basically.
Yeah. I mean,
Yeah, okay, but this is you need to prove it, right?
You need to prove it, but yeah.
But that's a very good counterexample, which is in fact countable, and it's finite cofinite.
From the natural numbers.
Yeah, for natural numbers. Yeah.
Yes, but so what I want to do is my argument would have been that remark basically, or rather observe that power set x, this Boolean algebra, I'm not going to write the operations, I'll just write power set of x. This is a Boolean algebra. It's basically always complete and atomic. So meaning that in this Boolean algebra, arbitrary joins in meet exist. And in fact, each element in this Boolean algebra is the join of the atoms below it, where the atoms are just the singletons. And you can just show that this property is preserved under isomorphisms. And however, there are Boolean algebras which are not complete and atomic, which is probably the one that you have.
I mean, it is atomic, but not complete.
Okay, so what is your Boolean algebra? Because I just realized that I did not even think about an example. But
yeah, so take all the finite and cofinite sets of natural subsets of natural numbers.
So you take the collection of.
You take the subsets of natural numbers, which are either finite or cofinite.
U is finite or U cofinite.
And this is nice because this is essentially the pro-finite Boolean algebra. If you take the co-limit of all the finite ones.
I see, yes.
Direct co-limit, we get this.
I mean, one has to think a bit why that is a Boolean algebra, I guess. It's definitely the complement is fine. Intersection and union, you just have to
like
check it.
they're a bit subtle, but you need to.
And then the rest is also clear. It's the full set and the empty set. Okay, good. This is one which is not complete. Okay, so therefore, the answer is no. But we still want to. So
Yes.
Oh yeah, that's what I was about to say. Very good. If that was a talk situation, but now I'm kind of skipping too many slides. But if I'm running out of slides, I will come back to this. No. So this is indeed not a problem for finite BAs. So note, we have that fin set. So if we take the category of finite sets, and we take the category of finite Boolean algebras, then we get a functor which maps a set to the Boolean algebra. However, that functor should be either written like this or with a non-cal p. It's not the covariant power set, but the contravariant power set. So this should be. Sorry, what?
You can also put a little cross on the tail.
Yeah, I mean, you could do a lot of things, sadly. That's what happens in the literature. That's why nobody knows. No, I mean, everybody knows. Anyway, so this maps a finite set to the finite Boolean algebra, which is given as a power set. And we can go back with question mark. What is the question mark? So we want, so there is, let me write it down, there is a dual equivalence. So these are equivalent categories. It's a dual equivalence because these are two contravariant functors. And so what does it mean? For example, we would want to have, we have the identity functor on fin set. We would need a natural transformation into this, right? The composition of those functors. And vice versa, we have it in BA should be the same as going like this. Sorry, this is not good. Ah, yes, it's good, but 2 and question mark turns out to be a very bad notation. I'm going to remove the question mark in a second if somebody of you tells me what the question mark is, basically. Sorry? Indeed, thanks. So the question mark here should be the atoms. So if you take X, you take the power set, you want to go back to X, right? Which are exactly the atoms in a way. And similarly, you can take first the atoms and then take the power set again. But important for this to be an isomorphism is that actually each element is characterized by a set of atoms. Otherwise, it doesn't really work. Okay, so what did I want to say about this? Atoms. So the only remark is, which I briefly realized in the last hour, it's not entirely obvious how this thing is defined on morphisms, right? Because, so this maps a Boolean algebra to the collection of atoms. Do you want to know what an atom is, or do you know what an atom is? An atom is basically an element in the Boolean algebra which is not 0, but whenever something is below it, the thing below is either 0 or that element. There's nothing really in between the atom and the bottom. So that's why it's an atom. You can't kind of split the atom. Only in real life. Sorry, what? But so there is, of course, a question: if I have a morphism from F A to B, what's the morphism that goes from atoms of B to atoms of A? And this is not at all that obvious. I mean, basically, okay, or is it obvious? I mean, basically, this definition that I'm writing down in a second is the only one that kind of you can come up with. But then you would have to still prove that it's actually correct, which I'm not going to do, I'm afraid. So we map an atom B to, I think, the smallest element A. Such that, okay, now in even, yes, such that B is smaller or equal than F of A, I think. Let me verify this. Yes. I mean, and then you would need to verify that this is an atom in the Boolean. But it's surprisingly, it's kind of funny because you could define that functor just in the way that we're going to define it in a second, and then it's much easier to define what it does on morphisms. But
no, this makes a little sense.
Okay, go ahead.
Because what you really, so of course you want it with ultrafilters, right?
Yes, indeed.
But in a complete atomic Boolean algebra, if you take any ultrafilter, it is principal, and the generating element is its meat. And so here's what you're doing is you take the ultrafilter that you get from the principal ultrafilter generated by B, and then extract the atom that generates it.
Yes.
So this is kind of what you're doing.
Okay. Okay, so this is in any case the finite Boolean, the case for finite. So this is kind of discrete Stone duality, if you wish, for finite Boolean algebras, right? There is another version of it, which is, you could also do the same thing, but just then with set. And however, then you write here indeed kappa for complete atomic. And here at. And then this is also an equivalence. But now we are not anymore restricted to finite sets, but we are now restricted to complete atomic Boolean algebras. So now the question is, how do we get actually a duality where we get the Boolean algebras on that side rather than anything else? Okay, let's keep this for a while. Maybe we will come back to this. And in order to the strategy to actually getting a duality with Boolean algebras is now that we want to have a way of getting to a nice collection of sets as a not power set of X, but some kind of sub-algebra of the power set of X in a way. So we want to kind of restrict to algebras that are not the full power set, but somewhere restricted to a nicer collection. Nicer is probably the wrong way of putting it, but so in order to do that, we want to know what a topological space is. And I have all the details on my notes, but I guess most of you know what a topological space is. But let me just at least start writing it. So topological space is indeed a set equipped with a notion of an open, of what are kind of the open subsets of that set. Now, I don't know, I don't have a good intuition of how to explain it. I yesterday went to Steve Wicker's book about topology in logic, I think it's called. And so how does he explain an open set? An open set corresponds to an affirmative assertion. Affirmative means that as soon as you get an evidence, that means that it affirms that the assertion is true. There's something else called the refutative assertion, which is you get evidence, and that means that you have to refute the assertion. But the open sets correspond to affirmative assertions, so something like some people in Edinburgh like Glasgow. When you find the first person in Edinburgh who likes Glasgow, you know it's true, right? And the refutative would be all Glaswegians are heavy drinkers. How are you going to figure that out? Because yes, you get some evidence and you know it's not true, basically. That's why it's refutative. So now if we have this idea that you have, so we have, a set X and tau. Tau is a subset of the power set of X, basically. And this is the collection of open subsets, which correspond to affirmative assertions. Now, what such that? Okay, and now what does this thing have to satisfy? First of all, we chuck in the empty set and the full set. They are both elements of tau. Then if we have a finite collection of affirmative assertion, then this is by itself an affirmative assertion. So we can just say, so for U1, blah, 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 UN in tau, we have the intersection of the UIs is in tau. So we are closed on the finite intersection. And then for whatever UI, I in I, where I can be arbitrary. So this is now a subset of tau. we have that the union over all ui is in Tor. So this is just so basically we are closed. We have the full set and the empty set closed on the finite conjunction, closed on the arbitrary disjunctions. Okay, so this was just topological space. Then what do we need as well? We need, when is a topological space Hausdorff? Hausdorff means what? It's also known as the T2 axiom, I think. So it means just that, so X Tor is H if, and then what? Indeed, if for all x1, x2 in X, there exists u1, u2 in Tor. That's that. Sorry, what? Yes, you're right. Such that x1 not equal to x2. This is very. This feels like fixing a car or something. Such that xi is in ui and u1 intersected u2 is the empty set. This is just, so basically we are just able to distinguish points with the open sets. And then we want something else. We want compactness. Oh my God. Now that reminds me of something I wanted to clarify. Anyway. What do I want to talk? Very good. I have here the definition for compactness, which just says ... I would be happier to do that in words, but I can't write it out. So what it means is that any cover of the whole set by elements of Tor contains a finite subcover. So whenever I can cover the full set with a collection of open sets, usually infinite, I can then find a finite subcollection which already covers the full set. Are you happy with this, or do you want me to make my fingers dirty? So this is, I'll do it exactly like in my notes, right? Let's stick to the script. And the final thing is, which is the most mysterious notion, and now there will be an avalanche of questions which I cannot answer. But I have a funny quote for that. But anyway, so zero dimensional in this case just means a basis of Klopen subsets. So I should explain that elements of Tor, or the elements which are called open, the complements of those elements are called closed. If something is both open and closed, then they are called Klopen. And so zero dimensional means that we have a basis of Klopen subsets. What is a basis? A basis means that every open set can be written as a union, possibly infinite, of elements of the basis, in this case, of the Klopen subsets. And when I was a PhD student, I asked somebody, but why is it called zero dimensional? What does it mean? And the answer was, as far as I know, there are 3 notions of dimension in topology, but for the case of n equals 0, they all coincide. So I still don't exactly understand why it is called zero, because I never really figured out what the definition of the dimension is we're talking about.
Separated.
Totally separated rings for me, as it involves some countability or not, but maybe not.
You're defining a Stone space.
Yes. Yeah, I mean, basically the thing that I'm going to say in a second is that the topological space satisfying those things is called a Stone space, yes.
See it totally.
But okay, yes. Yeah, I think so. I think also
Oh,
in
I
the
think wait, that's totally disconnected.
totally disconnected, yes. Yeah, totally disconnected, I think, yes. You have a question? No.
A very general definition. This one involves looking at collections of open sets and how the intersections play together. And so if you have, for example, the 2D space, you can detect this because you basically get like a Venn diagram of 3 open sets in a 2D space, and you can't get the Venn diagram of 4 open sets.
I see. Nice.
This is one way you could in 0-dimensional.
Okay, nice. Thanks. Okay, so this leads me now to the definition of indeed. Okay, this is now going all away, I guess. There's both good and bad news, I think. And it's the same, namely, I'm running out of time. I mean, anyway, so definition is indeed X Tor is a stone space if X Tor is whatever we called it, Hausdorff. Okay, this is a very bad way of putting it, but anyway, compact, 0-dimensional. Sorry, and the comma is to be read as an and. This is what's called a stone space. And now I could either be very, very brief or not. Let's not be too brief. So now, this is our candidate for duality. I mean, this is what we're going to show. We show that stone spaces will be dual to the category of Boolean algebras. And we already, given that we have a basis of clopin subsets, we already have a candidate for the functor in one direction, right? Because we start with the stone space, we just map to the clopin subsets. The clopin subsets are a Boolean algebra. So this gives us the Boolean algebra. The first question is, how do we go back from the Boolean algebra to the stone space? So what are the states of the stone space that we are trying to construct? And now the idea is that a state kind of corresponds. So a point of the space corresponds to a maximal collection of properties that are encoded by the Boolean algebra. So if you think of a Boolean algebra as a collection of property, then a state is just kind of a maximal collection of properties describing the state. So in some way, if you think of a state for each of the properties in the Boolean algebra, you say, are the properties true or not? And this leads us to the definition of an autofilter. And there's the usual definition of the autofilter. I mean, first of all, the usual is already a lie. There are like probably at least 3 of them or something, which then, of course, are all luckily equivalent. And there's the very simple definition of an autofilter. Let's first do this the hard way. So, over a Boolean algebra B, let's say. So we call U, which is a subset of this Boolean algebra, an ultrafilter. If. So I think the first property is that U is not the antiset. Curious, I might now add too many properties, but one is that U shouldn't be the antiset. And I think I also need to require that 0 is not part of U. So it's a proper filter. We don't want to include everything into it. Then 2 is it's upward closed. So, i.e., if x is in U and x prime is, okay, stupid, x is smaller or equal than x prime, then x prime is also in U. And then finally we have, what do we have finally? But we need this kind of, no, we have actually yet two more properties, I think. This is crazy. So, first of all, if x1 and x2 are in U, then x1 and x2 are in U. So basically, I think until here it's a proper filter or something. And then we need the last one, which usually ensures primeness, but because we're in a Boolean algebra, it even ensures maximality. And it's the one which says if x1 or x2 are in the filter, then either x1 is in U or x2 is in U.
It's not really an either.
I mean, I was just wondering, with either I don't mean exclusive or, that's the question. It's just like, then at least one of the two are in U. So does either express exclusivity?
Yeah.
Okay. Anyway, so this is this. And now we could actually prove something about it, but maybe not. So so this is an autofilter. The alternative definition would have been that U is an autofilter if we look at the characteristic function, so to speak, of U, which goes from B to 2, is an element of BA, right? So basically, is a Boolean homomorphism. So we have the two-element Boolean algebra. Then, and then the Boolean algebra. So basically, U is an autofilter exactly if it corresponds to a Boolean homomorphism into 2. Which is nice. I mean, okay, this is also something which you never forget in a sense, but this is something.
There's on the other side, there's of course the same thing.
Yeah. I mean,
Which is
but I forgot the actual term that we nowadays use for this.
It's an ambimorphic module.
Ambimorphic.
Yeah, it's an ambimorphic module, and indeed, because a Klopen subset is just
Yes.
Ambimorphic module. So the two is both a Boolean algebra and a Stone space.
Yeah.
And
The point is what
homing
we,
into it induces this dual adjunction between the two things.
what we actually get here is indeed like hom into 2.
Yes, that's what it was.
Did you just say the S word anyway? Indeed. So there is this book, the paper by, what's his name? No, but there's also, there's this German guy, Porst and somebody else.
Oh, Porst and Tolan.
They have, Porst and Tolan, they have this statement about this dualities induced by a ambimorph.
Like this is testing. Oh, no, sorry. This testing semantics is a different one. But yeah, Porst and Tolan.
So basically, you can go in both directions by homing into 2. Yes. So the funny thing is that the 2 lives on both sides. Yes? And this is a phenomenon which occurs much more frequently, but this is one particular example.
Indeed, there's like a nice theorem that says that if your categories are okay, then any dual adjunction arises in this way.
Yes.
If your categories are good enough, then any I don't know what the conditions are exactly, but if they're good enough, then any contravariant adjunction like this, just like doesn't even like you just need to be equivalent. Any contravariant adjunction arises via this kind of ambimorphic module.
So A fun fact about ultrafilter is still that it has a property that for each element in B, either that element is in the ultrafilter or its negation, which can be quite easily proven. I mean, there are lots of fun facts we could go about this. Like, for example, the compactness. So we will go from Stone to BA by going to the Clemens, right? By mapping the Stone space to its Clemens basis. And so one reason why that is well defined, in fact, is that if you have a compact space, you can show that there is only one Clemens basis, which is also very. So then if you say take a Stone space, we take its Clemens basis. That's just the one which is there because there's only one such thing, which is nice.
The non-constructive part is.
You're waiting for the non-constructive part. Yes. There's.
Ultrafilter lemma.
Yeah. So the non-constructive part. So first of all, actually, it was a bit surprising to me that I've had the trouble to exactly understanding what the non-constructive part is. Let's first briefly see whether we are completely at home already before we go to the non-constructive part. So if you have a Stone space, let me just briefly describe without proof what those functors are, right? So this is going from the Stone space to the algebra. We can call that already Clemens because this is just the Clemens. And from the Boolean algebra, we go to the Stone space, call this S. So if I have a Boolean algebra B, then what is now the Stone space? The Stone space is given by the ultrafilters over B, so the collection of all those things. And then the topology generated from a basis B, where the basis is now the Clemens basis that I'm about to define. It's the collection.
Don't call both B. This is confusing.
Okay, a B is bad. Well, what do I do? Boolean algebra basis, bad shit. I don't know.
Beta.
Oh, beta is not so bad, in fact. But beta is, of course, also.
Yeah, it is bad because
it's evil, but.
yeah, it's a bad choice.
This is normally the monad for which compact Hausser spaces are the algebras, but.
Yeah.
Anyway, so beta is just the collection over all B hat, B in B, with B hat is the collection of all ultrafilters containing B. Sorry. So we are given this collection of ultrafilters. Each element of the Boolean algebra defines me a collection of ultrafilters, which are those ultrafilters that contain B. And this is the Clemens. This is a Clemens. If I add this to the topology, it will be Clemens because the not B hat will be just the complement of this. And so we take as the basis just a collection over all those B hats and then generate a topology of it. And this will be the Stone space corresponding to B. And it's not difficult to see if I now take the Clemens, I will just get the element of B back, essentially, because these are just the Clemens by definition. And here we just go with the Clemens. And that's basically it. Right? Okay, so now the question was, where is the non-constructive argument? And the non-constructive argument is in two places, I think. But it's essentially always the same argument. But proving that this thing here, proving that this functor is well defined is kind of trivial because you just take the Clemens basis and what? I mean, you just have the Boolean algebra. But going from here to here, you need to prove that this is now a space which satisfies those axioms. And Hausdorff is easy. Zero dimensionality is also easy by definition. But compactness is difficult. And for compactness, you need indeed a non-constructive argument. And essentially what you need is the following statement. I wonder whether I can. For some reason, I did not make notes about the main statement. So this will be maybe a joint effort and the last thing that we want to do, which would be kind of called a lemma, I guess. And we say, so let B be a Boolean algebra.
Let B be ABA.
Yes, whatever. Okay, sorry, let B be ABA. Let, I don't know how I would want to call this. V be a subset of B. Such that for all finite V prime subset of V, we have that the conjunction of V prime is not 0. Then there is an ultrafilter.
Yeah.
U such that V is a subset of U. And this is the thing where what you need everywhere, basically. You need to prove compactness. You need. Wait, where else did I need it? I need it, for example, if I then want to use the whole thing to show some kind of completeness of the logic, whatever. In this case, it's you don't use this duality normally to prove completeness of propositional logic, but I think you probably could do it, and then you would also use this lemma here. But in any case, this is the non-constructive part of it. And so the approaches that I know that try to avoid this is, for example, the one that I know better, but I still didn't study it fully, is what's called possibility semantics, where they're working not with states, meaning fully specified things, the ultrafilters, but they work with the possibilities, which are kind of partial informations, which do not tell you for every element of the Boolean algebra whether B or not B is true. But I don't know then how they actually set up the duality to make it true, but they use this to come up with a kind of version of the duality that works basically without the axiom of choice. Whereas this one, okay, the proof of this is very easy, right? Because you just have to meet the conditions for the Sorn's lemma, which is kind of trivial. Because these things are clearly, if you have a chain, the join of this chain will be of the right property, but it's not really. We'll have again the same property, and that's why you need to know that there's a maximal element, and that this is your ultrafilter. But indeed, so what would be interesting indeed to understand the constructive approaches for avoiding this. But I mean, this is what I'm trying to do by reading the possibility semantics and so on. Now, okay, so I sketched how to move from here to here. And I'm running out of time now, basically. So I only want to say a few more things about this picture. So first of all, we started with distributive lattices. And we did not start with distributive lattices for nothing, in the sense that we can also take, instead of Boolean algebras, we take distributive lattices here. And then we want to write something on that side. And so in the literature, it turns out that there's actually then three options. But the easiest for us, in a sense, would be to write what's called Priestley space. I hope I write this correctly. Named after Hilary Priestley. And so the point here about Priestley space, Priestley. The point about those spaces is that is a Stone space plus an order, plus a partial order. And the idea is now that So the problem is like if we just have a stone space, we get a Boolean algebra, right? But now we have an ordered stone space, and we are now mapping here not to arbitrary clopens, but to clopens that are closed under this, upwards closed under the order. And this will give you a distributive lattice. And from the distributive lattice back, you're going to prime filters. Sorry, what?
Nothing.
And but then the morphisms are just order preserving continuous morphisms, which is kind of nice. There's another way of doing that by not going to the stone spaces plus an order, but to go to so-called spectral spaces, which is basically just the prime filters with some topology. Spectral, yes. And that's also, for example, described in the Stone Duality book by Johnston. Then you get just topological spaces, but the downside of that is that then the morphisms are not anymore just morphisms of topological spaces. Then you have to put some condition on the morphisms. And then actually, that's a good question. Given the fact that the morphisms are not anymore the top morphisms, I would say that this is probably not a subcategory of top. Whereas here, these are, okay, here you just get an additional order, but then the morphisms are just what you expect, continuous and order preserving. Okay, so that is one thing. The other thing is that you can indeed put Heyting algebras here. So you have a distributive lattice, but you also can define implication. And if you want to put Heyting algebras here, you would, one way is here indeed to put on this side, which is called Isakia spaces. There are again different ways of doing this, but Isakia spaces are Priestley spaces that satisfy one more condition. Namely that the downward closure of a clopen set is clopen. And at first it sounds weird, but then you realize this is exactly what you need to define implication. I see. It's obvious for some, but
No, it's not obvious. Maybe it's obvious for some.
yes. And then, however, if you then go here, you don't anymore have just the order preserving continuous, but you also need to add something to preserve the implication, which corresponds to the fact that if you are a distributive lattice and you have an implication, still, if you now have just a distributive lattice morphism, it doesn't mean that you're a Heyting algebra morphism. You need to also do something to actually preserve the implication, the additional condition. And actually, the condition here is that you also have to be a P morphism with respect to the order. Okay, so these are these things. And the final thing I want to say is that once we have a duality, right, the way that this is going very much around in my world, so to speak, is that we set something on top of it, right? So we have here the duality of stone and BA. But now on the BA side, I'm interested not in proposition logic, but I'm interested in modal logic. And so how do I get to modal logic? Well, the classical basic modal logic, the algebraic version of it is what's called a modal algebra, which is a Boolean algebra with an operator. That operator is exactly a semi-lattice morphism. In any case, you can define a functor on BA such that the algebras for that functor are exactly the modal algebras. And then you want to have based on this duality, you want to extend this duality to a duality between the H algebras and something on this side here, stone. And so what you get here is what's called the Vietoris functor. Vietoris, which used to be an Austrian topologist in Vienna, but I think by now he probably passed away because he would be now, I don't know how old. Anyway, so this is Vietoris. So the coalgebras for the Vietoris functor will be dually equivalent to the modal algebras. And you can then play that game. So this is all about dualities. it turns out, in fact, that actually it's almost at least as useful to look not in full dualities, but just establish dual adjunctions. And then work with dual adjunctions, because then you can do still a lot of things. And the idea is that if you establish dual adjunctions and you have functors on both sides and connect them in a nice way, something which is called a step, you can basically, first of all, well, you can study somehow properties of the logic with respect to the semantics, so to speak, by studying the relationship between those functors. And that's all I want to say, I think. Thanks. Good. Any questions? Was there anybody online? Just out of curiosity. Oh no. Hello. Yeah, so I don't know, like the Stone Spaces book by Johnston will not define stone spaces for much of the book. I think it's either a subsection somewhere or it is kind of really an exercise, because they work, of course, with locales and frames.
Yeah,
and do the whole thing on that level. But
I mean, also, I think they have like, I think chapter 1 is like introduction, and then chapter 2 is stone duality, and then they have 6 more chapters where they do all sorts of other
yeah, but
stuff.
also chapter 2 is stone duality. But if you know that stone duality, you don't necessarily recognize it immediately that that's stone duality. I mean, it is stone duality, yes, I agree. But
Yeah.
not in a simple
They
way.
do like Gelfand duality.
But if, for example, if you just want to know about lattices and you read the first chapter of stone spaces, it's funny enough already. It's a very good introduction to lattice theory, I think. And to the fact that how to get the implication on Heyting algebras and stuff like this.
I studied I studied the fact that this is non-constructive during my PhD qualifying exam. So I wrote a report. If you have outer filter lemma, you have compactness. There's another place where you need equilibrium. But I don't know if you can show numbers, like stone duality implies outer filter.
I see.
There's abstract stone duality from Algeria.
Yeah. That's the one thing I don't fully know, I think. The abstract stone duality. Yeah, I don't know. Maybe Fred knows because he was working in Birmingham. I mean, okay, the one thing I should say, one way this is used, by the way, is, okay, so just one more thing. So suppose we have a logic here given as a functor. The nice thing about that side of the world is that this is algebras, right? So then the logic directly corresponds to algebras in a way. So in a way, you have always soundness and completeness with respect to the algebraic semantics. It's like the initial algebra in a way, it gives you kind of the heart of the logic. So you map it over to here, which then gives you the canonical model of the logic, which is built on the outer filters. And then if you want to actually show that something that is consistent, a formula that is consistent, is satisfied in the model, you again need this lemma in a way, because as I said, you have a consistent formula. It will be an element of an outer filter, and therefore satisfied in that in that canonical model. Of course, you also have to prove that that is this thing that the lemma, which is like truth, is element of basically. So whatever is true at the outer filter in the canonical model is just the elements of the outer filter. And of course, there's some cheating happening in the sense that the initial algebra gives you the logic, but already modulo equivalence. So you're kind of working with equivalence clauses, even though you don't want to. But the Lindenbaum-Tarski algebra is Lindenbaum and Tarski. Excellent. Yeah, I don't know what else. That's it.
interestingly, if you read, I was just reading the Mathematics of Meta-Mathematics by Zagorski, and they have it in about Tarski algebra, but they don't do any quotienting. So it's not like it doesn't satisfy any of the equations.
Ah.
You know, so they just have, it's just in algebra instead of universal algebra, that like you have all of your syntactic operations, but they don't satisfy anything.
I should say that coming back to another Stone Duality talk that once happened at MSP, namely by Radu, I think, and because you mentioned Sikorsky,
Oh yeah.
Because everything is compact, that whole framework kind of intrinsically works for compact logics. But they were working, I think, with some probabilistic logics where you don't have compactness. But the claim is that they still managed to prove completeness using Stone Duality, but like a version of it which I still don't understand, to be fair. But that is kind of a challenge there, was to do this for a logic which is non-compacted. Which is?
So the algorithm dilemma is kind of tailored to the definitional compactness of K, right? But classically equivalent notions of compactness are not constructively equivalent. I can't remember
I mean,
exactly what they are now, but it's very challenging to change them. Maybe we could isolate all the non-constructivity of that equivalent.
Yeah, there's compactness of like any sequence is a convergence of sequence. Oh no, because that's not equivalent. But if you do this with, you need to do this with nets if you want it to be equivalent.
okay, that's a good question though. But one thing I would say is that this statement here is almost the definition of compactness. So you could, it's like, I think you could also define this to be compact if whenever you have a collection of Clemens that has the finite intersection property, it also has the infinite intersection property or something like this. I think this is equivalent to compactness, but I think the point is always whenever you want to show then that there exists an outer filter that kind of meets a certain property. I think you may, so that, okay, I don't know basically, but whenever you then want to have an argument that shows that there exists a certain outer filter, you will need some non-constructive argument, I think, irrespectively of which version of compactness you're using.
I think if you use the compactness with like universal nets, I think you get something very close, because I mean, I really don't remember that theory very well, but I think there was the sense that that definition of compactness already works with these really saturated kind of sequences, which already require all of the choice to be there. So it's the kind of. But it's harder to satisfy property, but it is more well tailored to constructively give you this. It's sort of where do you put the non-constructive bits?
Yeah. But also here's my confusion that I had when preparing this talk, and I need to think about it a bit more again. It's like there are two sources of non-constructivity. One is if you want to actually prove that the space that you get is compact. But the other one is once you want to show this kind of thing that if you have a consistent formula, it's satisfied in the canonical model, where you have to show that then there exists an outer filter in the canonical model satisfying this. Is it the same kind of, probably it follows from the same, it's just the same argument. Let me think about it. I was briefly confused about two sources of, which however all go back to that lemma here. So I don't know is the short answer to what you're saying. But I think it's not possible to avoid the non-constructivity without changing the setup, is it? And I'm just curious to figure out how they change the setup to make it work. But there are two options, I think. One is the possibility semantics, and the other one is the cover semantics. And I don't know how the cover semantics exactly works, but I think the cover semantics also goes away from states, but in a different way than the possibilities. But I need to double check how the. Yes. Thank you.